let me tell you about the gut-brain axis and our insatiable appetite for sugar and fat. Insatiable for sugar, unquenchable for fat. And this is a story about the fundamental difference between liking and wanting. Liking sugar is the function of the taste system. And it's not really liking sugar, it's liking sweet. Wanting sugar, our never-ending appetite for sugar, is the story of the gut-brain axis. Liking versus wanting. And this work is work of my own laboratory, that began long ago when we discovered the sweet receptors. And you can now engineer mice that lack these receptors. So in essence, these animals will be unable to taste sweet. A life without sweetness. How horrible. Okay? And if you give a normal mouse a bottle containing sweet, and we're going to put either sugar or an artificial sweetener, all right? They both are sweet. They have slightly different tastes, but that's simply because artificial sweeteners have some off tastes. But as far as the sweet receptor is concerned, they both activate the same receptor, trigger the same signal. And if you give an animal an option of a bottle containing sugar or a sweetener versus water, this animal will drink 10-1 from the bottle containing sweet. That's the taste system. Animal goes, samples each one, licks a couple of licks, and then says, that's the one I want because it's appetitive and because I love it.
So it prefers sugar to artificial sweetener.
No.
Equally
In this
artificial.
experiment, I'm going to put only sweet in one bottle, and it could be either sugar or artificial sweetener. It doesn't matter which one. Okay, we're going to do the next experiment where we separate those two. For now, it's sweet versus water.
Okay.
And sweet means sweet, not sugar. Sweet means anything that tastes sweet. All right? And sugar is one example, and Splenda is another example.
Aspartame, monk fruit,
You got it. All right?
stevia, doesn't matter.
Yeah, I mean, there's some that only humans can taste. Mice cannot taste because their receptors between humans and mice are different. But we have put the human receptor into mice. We engineer mice, and we completely humanize this mouse's taste world. All right? But for the purpose of this conversation, we're only comparing sweet versus water. An option, my goodness, they will leak to know from the sweet side, 10-1 at least versus the water. Make sense? All right. Now we're going to take the mice and we're going to genetically engineer it to remove the sweet receptors. So these mice no longer have in their oral cavity any sensors that can detect sweetness, be it a sugar molecule, be it an artificial sweetener, be it anything else that tastes sweet. And if you give these mice an option between sweet versus water, sugar versus water, artificial sweetener versus water, it will drink equally well from both because it cannot tell them apart. Because it doesn't have the receptors for sweet, so that sweet bottle tastes just like water. Make sense?
Makes sense.
Very good. Now we're going to do the experiment with sugar. From now on, let's focus on sugar. So I'm going to give a mouse now sugar versus water. Normal mouse will drink from the sugar, very little from the water. Knock out the sweet receptors, eliminate them. Mouse can no longer tell them apart, and they will drink from both. But if I keep the mouse in that cage for the next 48 hours, something extraordinary happens when I come 48 hours later and I see what the mouse is licking or drinking from. That mouse is drinking almost exclusively from the sugar bottle. How could this be? It cannot taste it. Doesn't have sweet receptors. During those 48 hours, the mouse learned that there is something in that bottle that makes me feel good. And that is the bottle I want to consume. Now, how does the mouse identify that bottle? It does so by using other sensory features. The smell of the bottle, the texture of the solution inside. Sugar at high concentrations is kind of goopy. Eh? The sideness in which the bottle is in the cage. It doesn't matter what. But the mouse realized there is something there that makes me feel good, and that's what I want. And that is the fundamental basis of our unquenchable desire and our craving for sugar, and is mediated by the gut-brain axis. The first clue is that it takes a long time to develop, immediately suggesting a post-ingestive effect. So we reason, if this is true, and it's the gut-brain axis that's driving sugar preference, then there should be a group of neurons in the brain that are responding to post-ingestive sugar. And lo and behold, we identify a group of neurons in the brain that does this, and these neurons receive their input directly from the gut-brain axis.
From other neurons.
You got it. And so what's happening is that sugar is recognized normally by the tongue, activates an appetitive response. Now you ingest it, and now it activates a selective group of cells in your intestines that now send a signal to the brain via the vagal ganglia that says, I got what I need. The tongue doesn't know that you got what you need. It only knows that you tasted it. This knows that it got to the point that it's going to be used, which is the gut. And now it sends the signal to now reinforce the consumption of this thing, because this is the one that I needed. Sugar, source of energy.
And are these neurons in the gut?
So these are not neurons in the gut. So these are gut cells that recognize the sugar molecule,
I see.
Send a signal, and that signal is received by the vagal neuron directly.
Got it.
And it sends a signal through the gut-brain axis to the cell bodies of these neurons in the vagal ganglia, and from there to the brain stem to now trigger the preference for sugar.
Two questions.
Yes.
One, you mentioned that these cells that detect sugar within the gut are actually within the intestine. You didn't say stomach, which surprised me. I always think gut as stomach, but of course, intestines.
They're intestine, because that's where all the absorption happens. So you want the signal, you see, you want the brain to know that you had successful ingestion and breakdown of whatever you consume into the building blocks of life. And, glucose, amino acids, fat. Yeah? And so you want to make sure that once they are in the form that the intestines can now absorb them, is where you get the signal back saying, this is what I want. Okay? Now, let me just take it one step further. And this now, sugar molecules activates this unique gut-brain circuit that now drives the development of our preference for sugar. Now, a key element of this circuit is that the sensors in the gut that recognize the sugar do not recognize artificial sweeteners at all.
Because their nutrient value is uncoupled from the taste.
Generically speaking, one can make that, but it's because it's a very different type of receptor.
I see.
Turns out that it's not the tongue receptors being used in the gut. It's a completely different molecule that only recognizes the glucose molecule, not artificial sweeteners. This has a profound impact on the effect of ultimately artificial sweeteners in curbing our appetite, our craving, our insatiable desire for sugar. Since they don't activate the gut-brain axis, they'll never satisfy the craving for sugar like sugar does. And the reason I believe that artificial sweeteners have failed in the market to curb our appetite, our need, our desire for sugar, is because they beautifully work on the tongue, the liking to recognize sweet versus non-sweet, but they fail to activate the key sensors in the gut that now inform the brain, you got sugar, no need to crave anymore.
So the issue of wanting,
yes,
can we relate that to a particular set of neurochemicals upstream of, so the pathway is, so glucose is activating these cells in the gut that through the vagus that's communicated through the, presumably the nodose ganglion and up into the brainstem.
Very good. And from there, where does it go?
Yeah, where does it go and what is the substrate of wanting? Of course, I think molecules like dopamine, craving, there's a book even called The Molecule of More, et cetera, et cetera. Dopamine is a very diabolical molecule, as you know, because it evokes both a sense of pleasure-ish, but also a sense of desiring more, of craving. So if I understand you correctly, artificial sweeteners are, and I agree, are failing as a means to satisfy sugar craving at the level of nutrient sensing. And yet, if we trigger this true sugar-evoked wanting pathway too much, and we've all experienced this, then we eat sugar and we find ourselves wanting more and more sugar. Now, that could also be insulin dysregulation. But can we uncouple those?
Yeah, I mean, look, if we have a mega problem with overconsumption of sugar and fat. We're facing a unique time in our evolution where diseases of malnutrition are due to overnutrition. I mean, how nuts is that? Eh? I mean, historically, diseases of malnutrition have always been linked to undernutrition. Eh? And so we need to come up with strategies that can meaningfully change the activation of these circuits that control our wanting, certainly in the populations at risk. And this gut-brain circuit that ultimately, it's the lines of communication that are informing the brain, the presence of intestinal sugar in this example, it's a very important target in the way we think about, is there a way that we can meaningfully modulate these circuits? So I make your brain think that you got satisfied with sugar, even though I'm not giving you sugar.
So that immediately raises the question, are the receptors for glucose in these gut cells susceptible to other things that are healthier for us? That's
very good. Excellent idea. And I think an important goal will be to come up with a strategy and identify those very means that allow us to modulate the circuits in a way that certainly for all of those where this is a big issue, it can really have a dramatic impact in improving human health.